Welcome to part 2 of Sea Ice Melt Explained. I will continue discussing with you research papers, back to slides, followed by concluding remarks. Here we go. Okay, I'm going to take a quick look in these next two ones here, what's going on at the Bering Strait side of things. And these papers published by Rebecca Woodgate. I have met her. She's an excellent scientist. She's an associate at the University of Washington. Actually interviewed there for a postdoc, and I decided to stay in Alaska. But she's a really nice, really nice person, very good scientist, and she's been doing the yeoman's work as far as figuring out what the flow into the Arctic Ocean from the Bering is, along with the heat documented. What I want to show you here is this is the transport. This is in sphere drops, so this is the flow through the years. This is the heat, and the heat is in 10 to the 20 joules. So 10 to the 21 joules would be a zettajoule. So this is almost an amount of zettajoules, an order of magnitude less. And as we see, the overall trend, if you look right here, is increasing. This dip here is interesting, and she discusses that in the abstract. But we see that the heat is increasing, the flow is increasing. She presents some mechanisms here, and you can see these are some heat signatures. So let's look at the highlights here. The Bering Strait inflow to the Arctic increased in 2001 about 0.7 sphere drops to 2014 about 1.2 sphere drops. This is due to increasing far field pressure head forcing, not local wind changes. Basically, you're heating up the oceans at lower latitudes. You've got pressure gradients that's affecting the pressure gradients, the gyrostrains, etc. Concurrently, heat and freshwater fluxes strongly increased, 3.5 times 10 to the 20 joules, 2,300 to 3,500 cubic kilometers. Seasonal data shows winter freshening, pre-summer warming, summer-fall flow increase. We present a new climatology for the strait, about one sphere drop, including seasonality for heat and fresh water. So let's look at the abstract. Year-round in situ Bering Strait mooring data from 1990 to 20, that's a 25, 26-year record, document a long-term increase about 0.01 sphere drops per year, about 0.2 sphere drops since 2000. So it's actually, this is again per year, in the annual mean transport of Pacific waters into the Arctic. Between 2002 and present, 2015, all annual mean transports except 05 and 12 are greater than previously accepted climatology. That's these dips here, right? Which is at 2005, there it is, and 2012, those were dips, especially the 2012. The record length maximum, 2014, about 1.2 plus or minus 0.1 sphere drop, is 70% higher record length minimum, corresponding to about a quarter-year reduction in the flushing time of the Chukchi Sea. Flushing time is when you are able to replenish the water. Think of when you hear, an HVAC systems. Whoa, we can have a turnover time of 3 hours for all the air. That means all the air in a room gets filtered through in 3 hours. So we're talking about, how long to flush the water, move it around due to current flows, mixing, etc. The transport increase results from stronger northward flows, not fewer southward flow events. The velocity distribution's annual mode ranges from less than 25 centimeters per second to greater than 40 centimeters per second, 60% increase in speed, 150% increase in kinetic energy, a metric with scales of the flow's impacts on bottom suspension, mixing, and erosion. I'll explain that later when we go back to the graphics. record length trends in annual mean heat and freshwater fluxes driven by volume flux trends since warming freshening trends 0.03 plus minus 0.02 degrees centigrade Celsius per year. 0.06 plus or minus 0.05 times 10 to the 20 joules per year. 10 to the 20 joules per year. That's a lot of heat we're introducing into the Arctic Ocean from the Bering side, on the Pacific side. So basically, we're ending up, it continues to, we have the highs in 07 and 2015, about 5.5 times 10 to the 20 joules, and they have some freshwater range. High flow year, anomalously weak, make sure I'm not skipping. High flow year, I did skip a line, was about 1 sphere drop, has the highest annual mean temperature recorded. So what she's saying here is when the flow is highest, is when we see the highest temperature, and then when we see the highest heat being introduced into the ocean. That is in essence what she is saying. Again, I will leave the URL so you can take your time and read this carefully. The low flow year was remarkably cold. Makes sense. You're not bringing in the warmth, it's going to get cold. What I want, the main point for me to show that I want you to take away from here is that the flow through the Bering Strait into the Arctic Ocean is increasing. So we're seeing an increase in the flow strength, 1 sphere drop. And the water is warmer, and it's bringing in more heat content. Hold that thought. Okay, so this was 2015, 2016, submitted, and it was published in 2018. Her latest, just published in April 2021. Warming and freshening of the Pacific inflow to the Arctic from 1990 to 2019. So that's basically a 30-year period, implying dramatic shoaling and Pacific winter water ventilation of the Arctic water column. Ventilation is just a way to it's a fancy way of saying vertical, overturned vertical mixing of the water column. Now, this model, this diagram here is very important. I want you to keep this in mind when we return back to the slides. PSW is Pacific summer water. PWW is Pacific winter water. So it's about 0.4 sphere drops. This is in the 1990s. Winter water is about 0.5 sphere drops, a little more in the wintertime. In 2014 and beyond, it's increased from 0.4 to 0.7, almost doubled. The winter water stayed about the same. It's that summer flow. And temperature about 1 degree C, about 4 degrees C. Wintertime's about the same, 1.9. So what are the highlights here? Bering Strait flow increases at about 0.1 sphere drops per year, cutting the Chukchi residence time by about 1.5 to 5 months now. So in other words, residence time refers to how long water stays in a region. That's what it refers to. We now have this water moving in. And so when it moves in, it's going to move the water sitting in the Chukchi. Now, Chukchi is basically cool water. So the residence time might have been about 1.5 months. When the flow is slow, makes sense. If the water flowing through the Bering Strait is not much volume, it's not going to move much of the Chukchi water there. But now it's increased in its flow, in how much is being brought in. So therefore, it's cutting down, it's reducing how long that cold water in the Chukchi sits there. When if you look at some of my earlier videos that I have done, and even my earlier recent video, when I do the sea ice updates and stuff like that, I'm always showing you how the ice is really disappearing in the Chukchi. I've discussed with you how the Chukchi is going to be kind of ice-free soon. That's because of this right here. We got this warm water that's moving more volume in through the Bering Strait. It's a lot warmer, so it's just displacing the Chukchi. And if the water is warmer, it's going to do what? It's any ice that maybe there's going to melt there. The warm water it's going to have to cool down more before it can start freezing. So this is why we're seeing the sea ice being lost in the Chukchi, because it's all warming up. Spring-fall warming, about 0.1 C per year, yields monthly means 2 to 4 C above climatology. That was above the record, above average, above the mean. Warm waters persist for more than 7 months. Previously, it's 5.5 months. Let me repeat that. Warm waters persist for more than 7 months. That's more than half the year. That's leading us to BOEs, Blue Ocean Event. This is why you got this warm water moving in through the wintertime and in the summertime, all year long. This is why the ice is melting earlier. Pacific winter water freshening shows the Arctic ventilation so that Pacific winter water no longer renews the cold halocline. In other words, the halocline kind of stays entrenched. So on this side here, they give you the abstract. Annual mean temperatures warm significantly with faster changes in June, July, cooling, so on, which is now 2 to 4 degrees above the record, the average record. Dramatic winter only, January to March, freshening, and PSU, that's units of salinity, makes winter waters fresher than summer waters. The resultant winter density change, too large to be compensated by Chukchi sea ice processes, shoals Pacific winter water equilibrium depth in the Arctic from 100 to 150 meters to 50 to 100 meters. In other words, it gets shallower, implying Pacific winter water no longer ventilates the Arctic cold halocline at 33.1 PSUs. PSUs, practical salinity units. Okay, plain language summary. The Bering Strait is the only oceanic link between the Pacific and Arctic Oceans. Typically, northward flow through the strait carries nutrients, and we're not going to be worrying ourselves about the nutrients, but that, of course, is important for productivity. The flow varies seasonally in temperature, salinity in spring, summer. Spring, summer brings warm waters that start the melt back of Arctic sea ice. In winter, it carries cold waters that traditionally sink deeper into the Arctic, well below the summer waters. But the annually serviced instrumentation, moored to the seafloor, measured the flow and properties in the strait, and they found that the flow is increasing significantly, reducing by about 1.5 months the time it takes to reach the Arctic from the strait, which is now 5 months. Summer waters are now 2 to 4 degrees warmer than typical, and warm for longer, 7 months compared to 5 months. So it's starting early and going longer. In winter, waters are dramatically fresher than before, now fresher than the summer. This change means the winter waters can no longer sink so deep in the Arctic, sinking only 50 to 100 meters as opposed to down to 150 meters. This not only means oceanic nutrients available close to the surface, but may also restructure how the upper Arctic Ocean mixes. So, and then she goes on to share some figures with you. Here is the heat flux. There's that 2012 low, but you can see how it is really increasing. So the main point is that the warm waters are now persisting for 7 months. That's why the ice, that's one of the reasons, in addition to melting the sea ice and absorption of the sunlight energy, but you have all this warm water input, not only from the Atlantic side, but from the Pacific side, that's bringing all this heat. We saw on the Atlantic side, it was terawatts. Terawatts is 10 to the 12. This is 10 to the 20. So that's 8 orders of magnitude more. That is a lot of heat. That is going to affect what happens to the ice, to stratification, productivity, etc. I said main focus on this presentation is why the sea ice is disappearing. Freezes later in the year, melts earlier in the year. This is a big piece of that puzzle that I've shared with you here. This is one of the articles. I'm going to do a deep dive later on, but I just want to hit some highlights here. Results from this model coupled climate, the NORA ESM1-M coupled climate model were used to examine relations between Arctic sea ice area and ocean heat transport through the primary Arctic gateways: Fram Strait, Spitsbergen Strait, Barents Opening, Bering Strait. Comparisons were made with two other models, CNRM-CM5, MRI-CGM3, all part of this modeling system going. Based on an evaluation, was the NORESM1M was found to be best suited to study the effects of heat transport on sea ice area. Inclusions are based on the results from that model. They divided the Arctic Ocean to the Barents Sea and the Central Arctic Ocean. The sea ice variability was further analyzed in terms of frazzle and congelation growth. Frazzle ice, when sea ice starts forming, you first gets called greasy ice, kind of looks like grease, and then it becomes a frazzle, and then it becomes pancake ice until it kind of gets into solid freeze up. A whole bunch of sequences in ice. Heat transports in the Barents Sea opening, the BSO, and the Fram Strait, the FS, and the Barents Sea. Increased heat transport in the BSO has a strong influence on sea ice in terms of basically reduced growth of the ice forming, the ice congealing, basically. So in the Barents Sea, right? Increased heat transport has a strong influence on sea ice area in terms of it forming, while bottom melting is important to the variability in the Central Arctic Ocean. The negative trend in sea ice area is considerably greater in the Barents Sea than the Central Arctic Ocean, despite the Central Arctic Ocean area being much larger, and reflects the major trend in the BSO heat transport. Okay. Don't forget, the Barents Sea has a shallow shelf, so the heat gets transported onto the shelf, then it diffuses from underneath. So I'm not going to go through. What I want to show you here is this table. Estimates of poleward heat transport in terawatts from various studies based on various models. So the BS is the Bering Strait. The BSO is the Barents Sea opening. CN is the Canadian Archipelago, Narrow Strait. And then we have the FS, the Fram Strait. So when we look at this here, at this table, these values are all in terawatts. So multiply everything by 10 to the 12th in terawatts. Okay. And what they've done here is from these various studies, they calculated a mean. So from the Barents Strait opening, it's 79.6 plus or minus 13.4 terawatts. Through the Bering Strait, 5.6 plus or minus 3.2 terawatts. Okay, seems to be in a bit of disagreement with what Dr. Woodgate was reporting. But look at these papers: 75, 91, 62, 87. These are old papers. So you can take these values with a massive grain of salt. I am inclined to discount these results and go with what Dr. Woodgate reported because of better technology, better analytical methods, etc. And then when I want to show you the Fram Strait, about 30.8 plus or minus 20.4 terawatts. So why such a large plus or minus? Because it's reflecting the seasonality, is what it is. So this is showing you some of the heat that some papers are reporting that goes into the Arctic Ocean. This is a paper I'll do a deep dive on later. And then This one here, Atlantic water heat transport variability in the 20th century Arctic Ocean from a global ocean model and observation. Okay, this was published in 2018. This is another paper that I will do a deep dive on later on as a separate video. The videos I'm going to do the deep dives on these papers will be their own separate videos. I mean, they present a lot of material here, so it takes some time to go through it. So let's see what the abstract says. The Northwood Ocean heat transport and its variability influence the Arctic sea ice cover, contribute to surface warming or cooling, or simply warm or cool the Arctic Ocean interior. Okay, so they're looking at the model. The model shows large decadal fluctuation in the ocean heat transport, with the largest variation in the Atlantic sector. The simulated net poleward ocean heat transport over the last century is about 68 terawatts. 88% of this occurs in the Bering Sea opening, about 45 terawatts, and the Fram Strait, 15 terawatts. Typical variations of 40 terawatts over time scale between 5 and 10 years, related to thermohaline and wind stress forcings. The main heat transport in the Davis Strait is about 10 terawatts. Less than 5 terawatt flows north in the Bering Strait. The core temperature of the Atlantic water entering the Arctic Ocean has increased in recent decades, consistent with an ongoing expansion of the Atlantic domain, the Atlantification that was seen happening in the Arctic Ocean. For example, Atlantification of the Bering Sea. But earlier warm events are also documented. The temperature of the northward flowing Atlantic water thus plays a vital role with decadal variation around half a degree Celsius. The Nordic Sea's atmosphere contributes with thermodynamic forcing, dampening the advected heat anomalies. That's a reference to the low and high pressure air systems. Variations in the inflow volume flux dominate, while variations in temperature dominate the heat transport in the Fram Strait. Okay? Well, Fram Strait's kind of narrow, so you're going to see more variations in sphere drips going in through the BSO versus, and where the Fram, you're going to see more variation in the heat. There are significant trends over recent decades, also dominated by the Bering Sea, that presently has one sphere drip higher volume transport 1 degree Celsius warmer Atlantic water than the long-term mean. Remember the specific heat content of water. That is a lot of extra heat energy now being carried by the Atlantic water. So they give you the abstract, and I just love this. Plain language summary. Ocean currents bring heat northward into the Arctic Ocean. Ocean heat influences sea ice cover. We find that ocean heat transport is varied at different time scales. These variations link to changes in wind systems, atmosphere, ocean heat exchanges, some extent local winds. Overall, the ocean heat transport and Atlantic water temperatures have increased during recent decades. These changes are especially large at the Bering Sea entrance, where the water has warmed by about 1 degree C. What's the take home from what these 6 articles I shared with you are? Transport in through the Atlantic side, into the Arctic Ocean from the Atlantic side and from the Pacific side, transport for the most part is increasing. Has increased, continues to increase. The water that's moving in is warmer. So that is also increasing. It increases the heat content. Okay, so now that we've taken a look at some of the papers, let's do a summary. On the Atlantic side, estimated flow volume, the annual mean flow transport, right? From that first one I shared with you, basically between 9 and 10 sphere drips northward. Estimated heat content, between 97 and 99, the annual was increased from about 16 to 41. Strong heat increase in the West Spitsbergen current. Mean values from 28 to 44. This is again terawatts. 2000, this heat is approximately 7.2 times 10 to the minus 10 fraction of the total heat content in the ocean that year, and with about 5 times 10 to the 22nd joules. By the way, in the old days, before we had word processors and superscripts and subscripts, stuff like that, if we wanted to write a power of 10, we use the capital E. So this is 10 to the minus 10. I don't know how much of a fraction of that total 5 times 10 to the 22 joules, or 500 zettajoules of heat energy. Okay? And going back to that, if you saw in capital letters EXP, that was E to whatever followed it. That's how we used to write it in the old days. Okay? The overall heat content in the ocean has increased greatly by at least 2 orders of magnitude. Think about that. 2 orders of magnitude. That is huge. So the Atlantic water inflow through the Fram Strait carries between 26 and 50 terawatts of heat into the Arctic Ocean as of 2016. All that extra heat is going to do something to the ice, as well as Atlantify the various regions of the Arctic Ocean. Okay, in 2018, 68 terawatts, about 80% to the Bering Sea, 12% through the Fram Strait. On average, one additional sphere drop of flow resulted with the Atlantic water on average about 1 degree C warmer versus long-term mean. Okay. Summary on the Pacific side. Estimated flow volume from 01 to 14, about 0.7 to 1.2 sphere drops. By 2021, I should put a space there, the flow through the Bering Strait had increased by approximately 0.1 plus minus 0.006 sphere drops per year. Estimated heat content, 01 to 14, about 0.06 plus minus 0.05 times 10 to the 20 joules per year. By 2021, the heat content is increasing approximately 0.05 plus minus 0.02 Celsius per year. Should have been period there. There is an increase in warm water duration in the Arctic Ocean from about 5.5 months to over 7 months per year. This is a really important point here. Preliminary examination data seems to suggest a relationship between how many sphere drifts flow into the Arctic Ocean and the heat content introduced. Makes sense intuitively. Heat and sphere drift appear to be somewhat cyclic, increasing and decreasing, usually closely tracking each other. Why is this? Not sure. That's what Dr. Woodgate's researching. And I hypothesize changes in the Arctic dipole, the Arctic oscillation, Pacific decadal oscillation, though the PDO has a periodicity of around 20 years. I'm just throwing out these hypotheses. But the important point is, if the water's temperature is increasing per year, it's the warm water duration is increasing to over 7 months. That's huge. Okay. Now, this is something I'm going to explain a little mechanism going on here. The Beaufort Gyre, by nature of its clockwise circulation, plus being situated over the Canada Basin, has the tendency to push or deflect surface and intermediate waters, particularly from the Bering Strait side towards the Eurasian side of the Arctic Ocean. This, plus the effects of an on-shelf Ekman pumping process and that mechanism, may deliver more warmer waters to the Eurasian side versus the North American side of the Arctic Ocean. These processes could be a possible explanation for why the Laptev, East Siberian, and Kara Sea, and the Barents Sea for that matter, are losing their ice far more rapidly. Look at the videos I've made when I look at the sea ice, when I discuss the sea ice, and I show you how the melting just disappears. It's starting so much earlier, and it's bam, it's practically going to where it's ice free, very soon. And we're seeing something again this year as well. Okay, so so think to all these videos showing. I'm now trying to pull this all together to give you the total picture. Everyone looks at the atmosphere. The oceans really is what drives things. So now I'm giving you the mechanism, or where all this heat's coming from, why the ice is disappearing, and I'm explaining a possible mechanism here. So compared to, okay, so we're seeing this processes, the movement of the warmer water onto the shallow shelf could be a possible explanation for why the Laptev East Siberian Kara Sea is losing the ice far more rapidly compared to the North American side. Why the ice melts earlier in the year, freezes later in the year. Though some of these waters are intermediate water layer, there is sufficient heat content along with the fusion processes that the extra heat now measured contained in these waters will diffuse upwards and melt the ice from below. So, before I go further, let's right? We went through those articles. I showed you the important values. Now, you got the water moving in, bringing in this heat. We know the oceans have been really warming up, from at all latitudes, right? I did the ocean heat content, 200 zettajoules, right? With 68% of that concentrated in the upper 500 to 700 meters. We got all that heat in energy. You got that heat moving, those waters with all that heat is moving into the Arctic Ocean. It's staying longer. It's warmer. The flow is increasing. So it's bringing more of the heat in there. Now it's going to diffuse upwards. And that heat is going to melt the ice from below, but it's also going to give off the heat to prevent the freezing later on in the year. So you're losing the ice. You got the heating from the sun, heating the surface waters. So you got the absorption of energy there. So that takes longer to cool down. And don't forget the specific heat of water. You got that going on, right? So it's taking longer to cool down. But now, as the surface water is trying to cool down, you're getting diffusion from below. That's keeping the water warmer. And it doesn't get it down sufficiently cold enough to start freezing until much later in the year. And that diffusion continues through the winter such that it diffuses upwards, and then in the springtime, it melts it earlier. So, here we go. Kind of 3D slice here. So you got the Pacific water inflow through the Bering Strait. It's coming in here. Okay. Here's the Beaufort Gyre, right in this vicinity here. And then there's all these various flows and so on. Here's the Fram Strait, export of sea ice and low saline waters out this way, right? Labrador Current. Before I explain what's going on here, these red lines here, these contour lines, see they got 25, 31, 30, what have you, 31. These are isohalenes. These are lines of similar salinities. So you got like 25, 26, 27, 28, 29, 30, 31, right? So these low values here are representing the riverine input. That's what this represents. Here's the Mackenzie River, right? You got the Lena River, the Ob, and so on. Here's your transpolar drift. Keep in mind, this is all shallow. So you got the gyre here. It's pushing the water, probably the warmer water, onto the shelf here. And if it's pushing it off, it's got to go somewhere else. Well, we're now seeing that it's not ventilating as well. So that actually might mean that the pumping could be slowing. But we're not ventilating. But here's the input from the Atlantic side. Okay. It gives off its heat. It becomes cold, but it's very salty, and it sinks. This is AMOC right there. Okay. So they're showing the average summer salinity. Purple is, and blue is less saline. You get up to the orange, the green, the orange, the red, that's extremely high salinity. Dashed line represents the halocline. And here's that surface, this freshwater lens on the surface from most riverine input, right? It's purple. So we're talking a salinity around 20. Then it gets a little higher salinity here, as the effects of the riverine input fade. They'll get up to about 31 point something, 32. Then we get to 34, and then we're getting into the 34.5 realm down to 35. So what this is showing is that the Atlantic water is more dense. So it sinks below the halocline. We're going to say, but wait a second, it's warmer water. Shouldn't that make it less dense? Well, it may be warmer water, but it has a higher salinity content. And in this case here, the higher salinity makes it more dense, so it sinks below the halocline. And as it turns out, this green is representing the Atlantic water. This light blue is representing the Pacific water input. Okay? Now, this is through the 60s and 80s. It has changed drastically since. Now, this is what I want to show you. Okay? This is the polar mix layer. This is all the mixing going on with the, say, seasonal sea ice melting, freshwater input, etc. Here's the flow in through the Pacific side. This is the Pacific halocline, a sharp change in the salinity. Here's the Atlantic halocline. Here's the input through the Fram Strait. Here's the Atlantic water. This is intermediate water. You'll see how the Atlantic water is more dense than the Pacific water, as illustrated here. Dense. Then you have this deep water. This water is so cold and the salinity has accumulated that it's dense. This Lomonosov Ridge prevents water to the Canada Basin to communicate or mix or interact with water in the Amundsen or the Nansen Basin, or basically the Eurasian Basin. Here's the Makarov Basin. Right? Doesn't ventilate. What Dr. Woodgate was talking about was the specific halocline not getting as deep, getting shallower. So you have this water now moving in at more volume, and it's warmer. It's going to do what? You got this heat here. The heat starts diffusing upwards, going through the halocline, getting it to then prevent the ice from forming or melts any ice that's already there. It will melt it. This kind of gives you a schematic of the water layers. This is Atlantic water becomes intermediate because it sinks. It sinks under the polar mix layer. It sinks under where the Pacific water influences are manifesting itself. And so, this is representing not only the surface, but intermediate water. These little things with the white, right, these things, these are the moorings. These are taking measurements. The red represents warm water. Okay, so you got this warm water moving in. Okay, moves in through the Fram Strait. This is the Bering Sea. This is the Bering Sea opening. This is the West Spitsbergen I've been talking about. You can see it gets a little lighter in color because it's cooling off. We got all these more Eurasian basin, all these different basins, right? Here's part of that flow. These little arrows, upward heat flux. There it is. Now, you've heard me in other videos talk about thermal inertia. And people say, oh, if we cut greenhouse gas emissions and stop burning fossil fuels, we can stop things at 2C. Well, the thermal inertia is not just only what's in the atmosphere because of the permafrost thawing and releasing the CO2 and etc. and the methane. The thermal inertia is the ocean heat content that I've been discussing. It is this ocean heat content that even if we stopped right this moment burning all fossil fuels, we're still going to have the thawing of the permafrost, but we're going to have all this heat, 68% of 200 zettajoules in the oceans, that's going to diffuse not only upward to melt the ice or prevent the ice from freezing in the first place, but all this heat will diffuse back into the atmosphere. There's your thermal inertia, folks. So the oceans have absorbed so much heat energy, and the oceans are moving. And guess what? Big surprise. Not all this heat's going to be moving into the Arctic Ocean, and it's basically going to cause loss of the sea ice. It's going to cause blue ocean events. And depending who you look at, someone now saying it might be a blue ocean event this summer. We'll wait and see. Models are saying 2022 to 2024, but by mid-2030s, the Arctic Ocean will be ice-free year-round. That has huge consequences for the climate. So this is representing all this heat that's being moved in, all the heat contained in the water. It's going to melt the ice. It's going to prevent the ice from freezing. And by the way, we see something similar in Antarctica with the shelf ice, heating from above, warming the oceanic waters and then these warmer oceanic waters is getting underneath the ice, on the shelf ice, melting it from below. That's a major reason why those ice shelves are breaking off. So in my ocean heat content video, okay, and we'll get to this in a moment, I explained to you that 93% of all greenhouse gas heat since 71 been absorbed by the ocean. And I shared with you how much the content is. I shared with you, I gave my explanation how this tells me that we're having a major stratification of the oceans, which in the long term is going to be bad for productivity, as well as the thermohaline flow is slowing down, if not probably has at least stopped to deep depth, and which means the sequestration of carbon and heat will stop, sequestration to depth. So I explained all that kind of as a setup for this video here, as to now what does it mean with all this heat? And all this heat is basically moving around, and it's affecting the sea ice in the Arctic Ocean. So possible model describing sea ice loss mechanism. This is what I come up with. Change in the lateral boundary conditions for sea ice movement. That's basically a reference to earlier when we talked about, melting the ice. More ice loss is seen on the shelves than in the open Arctic Ocean. Well, that is part of your you losing the ice at the edge on the shelf. The lateral boundary, think of the boundary current. Okay, so we're seeing a change in that. So we're seeing the ice melting on the shelf, which will affect what happens at the boundary condition. Boundary condition is where the shelf starts transitioning, going to the deep basin. So basically going from the shelf to the slope. Strengthening of the sea ice motions in upper ocean circulation. Well, if you got more water flowing into the Arctic Ocean, you're going to have stronger flows. And the stronger flows will, of course, affect how the sea ice moves about, along with what the atmospheric cells, highs and lows, are doing. Increase in oceanic transport, that's measured as sphere drops, tied into the strengthening of the upper ocean circulation. Warming of the upper ocean, the intermediate and surface waters, allowing heat to diffuse upwards, leading to ice melting from below or preventing of ice freeze up from occurring, especially the fact that now the resident time has increased to over 7 months. So now 7 months of very warm water, certainly warmer than minus 1.8 C, you're not going to have ice for too much longer. This leads to ice reduction, along with retardation of sea ice formation near the coast. Again, because of this upward heat diffusion. So, now you have the explanation. Now you know the mechanism for why the sea ice is disappearing. It is not just because of the sun energy input, but also because of the physics of currents and how the oceans have warmed up so much. And of course, we've got all these currents. The currents are carrying all this heat. They carry this heat into all over the planet. But we now know through flows through the Fram Strait, West Spitsbergen, and through the Bering Strait, have all this heat being introduced. The flow is increasing. The heat content is increasing because the waters are warmer and continue to warm. You bring in all this heat, the upward diffusion will melt whatever ice is there, and the upward diffusion continues such that the freeze up is delayed. This is what's going on. So you bring in the warm water, in like March, April, May, June, that kind of stuff there. You bring in that warmer water, it's melting the ice. The warm water stays. It stays there for over 7 months now. It delays the freeze up later on. Sun energy from above, heat energy, massive heat energy from below. Sea ice is disappearing. So there it is, folks. That is what's going on. So as I said, I will leave the URLs to those 6 links there, 6 articles we looked at, and 3 of them I will do a deep dive later on of them each on their own. But I will leave the URLs in a comment in the comment section, so you can click on and examine those papers yourself. So I hope you found this informative, and I hope now it has enhanced your understanding of what is happening, why the sea ice is disappearing, and why. We now know it's not just the sun, but the oceans. And I've been saying this, many people think the atmosphere is the driver of climate. It plays a role, but the major driver of climate for planet Earth are the oceans. And especially now when you consider the specific heat, when you think about, the waters going into the Arctic Ocean is warmed by 1 degree C. Think of the specific heat and all that extra energy that takes to warm up the water. That energy gets translated into extra heat into the Arctic Ocean. So you have warmer water getting into the Arctic Ocean, more of it. I showed you the sphere drops per second and the heat content per second, and that as well as annual values. So I showed you all that. That heat gets into the Arctic Ocean early in the year, so it melts the ice earlier in the year, and that warm water stays longer in the Arctic Ocean. That delays the freeze up later in the year, along with the heating from above, from the sun. So you take these things together, these 2 major mechanisms together, and this is why the sea ice is disappearing. Thank you for your time, and thank you for your patience in going through this lengthy material. Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.